When you're solving chemistry problems, conversions show up everywhere. Whether you're moving from grams to moles, liters to particles, or grams of one compound to grams of another, the process always comes down to carefully tracking your numbers, units, and compounds. This video is going to walk step by step through the process so you'll know exactly how to set up conversions and avoid common mistakes. When working with chemistry conversions, every value should have a number, a unit, and a compound so we can keep track of what compound we have and what unit we are in. Our goal is to create a unit map, write down the conversion factors needed, find the conversion factors from the periodic table if needed for the molar mass, start with a given value over 1, and then add in all conversion factors to cancel out units. This time, when we are canceling out units, we need to cancel out the unit and the compound together so they both match, like x's canceling out in math. Before we look at the examples, let's review the conversion factors that we will use in chemistry. Make a mini note card with these conversion factors. Molar mass is the number of grams per every 1 mole of a compound and is used to convert between grams and moles for the same identity. For example, if we knew that we had 3 moles of carbon dioxide, I could use the molar mass to convert to grams of carbon dioxide, or if I knew we had 20 grams of ammonia, I could use its molar mass to convert to moles of ammonia. Different unit, but same identity. To find the molar mass, we add up all the individual molar masses for the elements in the compound. For example, if I needed to know the molar mass for glucose, I would add 6 carbons, 12 hydrogens, and 6 oxygens together to get a value of 180.18 grams of C6H12O6 for every 1 mole of C6H12O6. Avogadro's number is the conversion factor used to go back to the real scale that particles are, very small. The number will always be the same and will allow us to convert between moles and molecules, particles, formula units, or atoms. The conversion factor is 6.022 times 10 to the 23rd molecules, particles, formula units, or atoms per every 1 mole. Any of those 4 words can be used to convert to moles, and this conversion factor will always keep the same identity. For example, if I knew I had 5 moles of CO2, I could convert to molecules of CO2 with Avogadro's number. STP, also known as standard temperature and pressure, is another important conversion factor. When STP is mentioned in a problem, we can use the conversion factor 22.4 liters per 1 mole to convert between liters and moles for the same identity of a compound or element. STP is used for conversions with gases, and we will see this concept again in the gases chapter. For all of these conversion factors, notice that moles is the middle ground. Like prefixes in the base unit in the metric system, we use the base unit to go in between prefix units. Now we are going to use moles as our middle ground to convert between atoms, molecules, particles, formula units, liters, grams, and so on. We also have to make sure the identity of the unit matches. For example, we cannot convert from grams of glucose to moles of carbon dioxide using a molar mass. We wouldn't know if the molar mass was supposed to go with glucose or carbon dioxide because they do not match. The only way to convert to a new identity will be to use a balanced chemical equation with a mole-to-mole ratio using coefficients for each. We will see this in the next video on stoichiometry. For now, we can convert to an element within a compound using a mole-to-mole ratio. We will always have 1 mole of the compound, and to find the moles of the element to use for the conversion factor, you just have to count the amount you have for that element in the compound. For example, I could convert from moles of glucose to moles of hydrogen by seeing that I have 12 hydrogens in the compound. The mole-to-mole ratio will be 12 moles of hydrogen for every 1 mole of glucose. We use moles to convert to a new identity because moles are our ratio unit in chemistry. Everything is equal in moles and on an even playing ground. What this means is that 1 mole of any substance, whether it's hydrogen atoms, glucose molecules, or oxygen gas, always represents the same number of particles, 6.022 times 10 to the 23rd. Even though the masses and volumes of different substances can vary a lot, when we talk in terms of moles, we're comparing them on the same scale. This even playing ground lets us line up compounds and elements fairly so we can use ratios directly from chemical formulas and balanced equations. You can think of a mole similar to the expression that we know when we say a dozen. A dozen apples and a dozen pencils are completely different objects with different weights and sizes, but when you say a dozen, you know you're talking about 12 of each. A mole works the same way in chemistry, except instead of 12, it's always 6.022 times 10 to the 23rd. That's why chemists use moles as the common language to make comparisons and conversions possible. We will go through each type of conversion in different categories. For each problem to solve, we will identify what value, unit, and compound we are starting with, and what value, unit, and compound the question is asking us to solve for. We will then connect the unit and compound together with a unit map. For each arrow in the unit map, we will put the conversion factor that we are going to use below the arrow to help organize the information. We can then set up the starting number, unit, and compound in a fraction over 1, and then set up all units to cancel out, making sure that the compound also cancels out and matches. We may need multiple steps because moles is our middle ground. If the starting or end unit is not moles, we will know that we need multiple arrows and multiple conversion factors in our unit map. If we are converting to a new identity, we will also need to be in moles to use a mole-to-mole ratio to get to the new identity. The first category is converting in between mass and moles. Mass has the base unit of grams, so we will use grams unless another unit is mentioned in the problem. For mass to moles conversions, we will use the molar mass. This question says convert 25 grams of NaCl to moles. For the unit map, we are given 25 grams of NaCl, and we need to convert to moles of NaCl. To convert from grams to moles for the same identity, NaCl, we will use the molar mass. To find the molar mass, I will add the molar mass of Na and Cl to get a value of 58.44 grams of NaCl per every 1 mole of NaCl. Setting up to cancel out units, I will start with 25 grams of NaCl over 1. In the next fraction, we need to cancel out grams of NaCl, so our conversion factor has 58.44 as the value attached to grams of NaCl, so I will put that on the bottom. We cannot split conversion factors up, so on the top of the fraction, I will put the other half of the conversion factor, 1 mole of NaCl. The grams of NaCl cancel out, and we are left with the unit and compound that we need for the answer, moles of NaCl. Dividing the values, we get 0.428 moles of NaCl. This question says how many grams are in 2.5 moles of H2SO4. For the unit map, we are given 2.5 moles of H2SO4, and we need to convert to grams of H2SO4. To convert from moles of H2SO4 to grams of H2SO4, we can use the molar mass because it connects grams and moles together, where we can cancel one of the units out to get to the other. To find the molar mass, I will add 2 hydrogens, 1 sulfur, and 4 oxygens. The molar mass comes out to 98.08 grams of H2SO4 per every 1 mole of H2SO4. Setting up all units to cancel, I will start with 2.5 moles of H2SO4 over 1. In the next fraction, 1 mole of H2SO4 goes on the bottom and 98.08 grams of H2SO4 on the top. The moles cancel out and we are left with grams of H2SO4. Multiplying the values, we get 245 grams of H2SO4. In this question, we have what is the mass of 0.75 moles of calcium carbonate? For the unit map, we are given 0.75 moles of CaCO3, and we need to convert to grams of CaCO3. To convert from moles of CaCO3 to grams of CaCO3, we can use the molar mass because it connects grams and moles together. To find the molar mass, I will add 1 calcium, 1 carbon, and 3 oxygens. The molar mass adds up to 100.09 grams of CaCO3 per every 1 mole of CaCO3. Setting up all units to cancel, I will start with 0.75 moles of CaCO3 over 1. In the next fraction, we need to cancel out moles of CaCO3, so I will put 1 mole of CaCO3 on the bottom and 100.09 grams of CaCO3 on the top. The moles cancel out and we are left with grams of CaCO3. Multiplying the values, we get 75 grams of CaCO3. In the next question, we have how many moles are in 150 grams of C6H12O6? For the unit map, we are given 150 grams of C6H12O6, and we need to convert to moles of C6H12O6. To convert from grams of glucose to moles of glucose, we can use the molar mass because it connects grams and moles together, where we can cancel one of the units out to get to the other. To find the molar mass, I will add 6 carbons, 12 hydrogens, and 6 oxygens. The molar mass comes out to 180.18 grams of C6H12O6 per every 1 mole of C6H12O6. Setting up all units to cancel, I will start with 150 grams of C6H12O6 over 1. In the next fraction, we need to cancel out grams of C6H12O6, so I'll put 180.18 grams of C6H12O6 on the bottom and 1 mole on top. The grams cancel out and we are left with moles of glucose. Dividing the values, we get 0.833 moles of C6H12O6. The next category is moles to particles conversions. And for moles to particles and particles to moles, we will use Avogadro's number because particles are very small and moles is our middle ground. In the next question we have, how many molecules are in 0.250 moles of CO2? For the unit map, we are given 0.250 moles of CO2, and we need to convert to molecules of CO2. To convert from moles to molecules, we can use Avogadro's number because it connects molecules and moles together, where we can cancel one of the units out to get to the other. The conversion factor is 6.022 times 10 to the 23rd molecules of CO2 per every 1 mole of CO2. Setting up all units to cancel, I will start with 0.250 moles of CO2 over 1. In the next fraction, I will put 1 mole of CO2 on the bottom and 6.022 times 10 to the 23rd molecules of CO2 on the top. All the moles cancel, leaving us with molecules of CO2. Multiplying the values, we get 1.51 times 10 to the 23rd molecules of CO2. For the next question, we have convert 3.01 times 10 to the 23rd atoms of helium to moles. For the unit map, we are given 3.01 times 10 to the 23rd atoms of helium, and we need to convert to moles of helium. To convert from atoms to moles, we can use Avogadro's number because it connects the two units together where we can cancel one out to get to the other. The conversion factor is 1 mole of He per 6.022 times 10 to the 23rd atoms of He. Setting up all units to cancel, I will start with 3.01 times 10 to the 23rd atoms of helium over 1. In the next fraction, I will put 6.022 times 10 to the 23rd atoms of helium on the bottom and 1 mole of helium on the top. The atoms cancel, leaving us with moles of helium. Dividing the values, we get 0.500 moles of helium.